Good morning, North America, and welcome to XJet's webinar, The Story of 10,000 Parts. We're so excited to have you all here. I'm Yael from XJet's marketing team, and I'll be your host today to guide you through our webinar. As what we mentioned before, this is our first ever virtual tour that is dedicated for the North American audience, following a successful event that we had, the same virtual tour with the European audience. So here we're bringing everything to you and for you to understand what we're doing about our technology, and hope you can get some inside understanding of XJet better than before. So in the upcoming 45 minutes, we'll give you a full show of XJet's capability of printing high quality industrial parts with straightforward processes and shorten lead time via 3 steps of print, wash, and sinter. Harry Danford, VP Sales North America at XJet, will open the floor today about the ceramic and metal AM market and about XJet, as well as the product overview of our ceramic and metal systems. The session will be followed by an immersive virtual tour to our additive manufacturing center, where Ron Fairmont, our AMC manager, will guide you through the production demo session and show you how our solution achieves industrial production capability at 3 steps without compromise on part quality. We have a quick Q&A session in the end for everyone for about 5 questions. Whenever you have questions throughout the webinar, feel free to drop them in the Q&A bar below, and we'll answer them either live or after this webinar. Our staff will follow up with you offline by email. Okay, so I believe we're good to go, right? Let's welcome Harry Danford, VP Sales North America, for an overview about the market, about XJet, and about the technology. Harry, the floor is yours.
Okay, excellent. Thank you, Yael. Appreciate the introduction. Hello to everyone in North America. To those of you who are on East Coast time where I'm at, grab yourself a sandwich and let's enjoy having a nice lunch and learn. If you're in the Central Time Zone or the Mountain region, or perhaps on the West Coast, grab a cup of coffee and get yourself a nice bagel for breakfast and enjoy our time together here today. So I just want to say thank you to everyone for joining today. We know everybody's busy, taking time out of your busy schedule just to learn a little bit more about our technology. We really appreciate, and we trust that that'll be an informative session for all of you. We just want to start with a very brief market update. We're not going to spend a tremendous amount of time here, but we thought it was important just to give you some perspective about how we see the markets presently and in the coming years, in the short term here. So you can see here, if you've been around the additive manufacturing market for any length of time, you'll recognize some of these numbers. We anticipate, based upon positive feedback from a variety of different applications and market research, that there will be really nice upside potential for the additive manufacturing market as we go forward here. So you can see the numbers on the left-hand side, the 2022 data, total market size for additive manufacturing, around 18 billion. The slice of that's a metal additive manufacturing market is around 5 billion, and about 250 million for the ceramic slice of that pile. Going forward, looking outward toward 2030 timeframe, we see the numbers here on the middle part of the slide, double-digit growth in all areas, up to around 73 billion in terms of the total market, and then 23 billion for metal, and really aggressive 3.5 billion for the ceramics. So we're really excited about both metal and ceramic, but as you followed the markets, one of the things you'll know and recognize is that really metal has obviously been leading the way for some time, along with plastics, polymer materials. We see ceramics as being a tremendous application with our technology, and you'll see that as we go through the presentation today. And then finally, if you go to the right-hand side of the screen, you'll see just some of the data on the systems themselves. In 2022, around 3,000 systems sold, and projecting toward in the range of around 16 to 17,000 systems being sold in the 2030 timeframe. All this data includes not just the systems, but obviously the materials, the services, the consumables, all the things that go along with the revenue generated through additive manufacturing. Just like most applications, we see the market verticals being very broad with our technology, everything from medical and healthcare all the way through electronics, aerospace and defense, consumer electronics, the energy sector, both oil and gas, as well as clean energy, automotive applications, kind of the standard typical market verticals that a lot of additive manufacturing is currently realizing good success. Just a few words about some of the applications that we're seeing. Some of these are already applications that we've progressed and commercialized in, and it's again very broad. Everything from medical applications where you have surgical instruments, where you need really high precision tools like surgical grippers, as you see here, high precision tooling like turbine blade applications for investment casting, consumer electronics, earbuds there. Aerospace and defense, we're excited about where our technology can play in terms of antennas and waveguides, and in the RF space, anti-reflective surfaces and such. So just a broad range of things. Sensor technology, temperature, pressure, oxygen sensors, whether it's downhole oil and gas or whether it's an automotive application, another nice area for a fit with our technology. Just talking about XJet here at a glance. So we've been in business for around 10 years. Right now, we're about 100 employees globally. You can see here we've generated in the neighborhood of around 80 patents. We've got a number of leading customers, everything from really small manufacturing, privately held companies to medium-sized tier 1 and tier 2 suppliers in the different market verticals that we mentioned earlier, all the way up to the large OEMs and major tier 1s for the major industries that we talked about. One of the things that we really pride ourselves on is the ability of this technology to really provide custom parts that are really filling a gap where other additive technologies are falling, I don't want to say falling short, but just where the capabilities certainly just not there. And you'll see that bear out here as we go through these slides. And then finally, we'll just mention the ability of this technology to do multi-material printing, which is not something that's really widely been commercialized in other additive manufacturing applications. And the future for multi-material printing is really compelling when you think about the possibilities of what can be accomplished. So here's the challenge part that we're going to talk about today. I think everybody, when you received the invitation, there was a story about a quantity of 10,000 parts that we were challenged with from one of our key customers. You can see here the geometry of this part. What it is it's an industrial nozzle. You can see the complex geometry, the internal channels with the sliced part that you see there on the right-hand side of the photo. And basically what this is it's a three-way nozzle for blending of different chemicals. And so they chose zirconia, obviously, for its material properties, for resistance to heat, resistance to corrosion from contact with chemicals, resistance to heat, so thermal conductivity, a key CTQ. And then the other thing that they were trying to do was, to generate 10,000 parts by a standard process like ceramic injection molding. Really, there were a couple of challenges. One was the cost of amortizing the tooling over that 10,000 part requirement, as well as the ability or the lack of ability to really produce a part with this type of geometry in a single piece. So with that, we'll transition over to just a discussion and an overview of what we call NPJ technology. And so what NPJ technology stands for is nanoparticle jetting. And so essentially what we do at XJet is we develop various materials that we incorporate into various ink systems that are really just jetted out of a standard print head. So we develop the ink formulations. Today we have three different materials that we're offering commercially. One is aluminum oxide, or 99.99% alumina. The second ceramic that we have is a yttria stabilized 3-mole zirconia, so YSZ, if you're familiar with that term. And then on the metal side, we have a stainless steel 316L. I've already mentioned a little bit, but we're multi-material printing, and what we're jetting, along with the nanoparticles of the ceramic and metal, are the water-soluble support structures. And so we'll see a little bit more of that in the forthcoming slides. What all that leads to is a really high resolution printing capability that yields really high-end quality parts with very fine feature resolution, very fine surface finish, and very precise dimensional accuracy. When you look at or listen to a lot of the other, let's just say, system OEMs that have other types of additive manufacturing technologies, what you'll oftentimes hear is they'll talk about the different part sizes that they're able to produce using an analogy of some type of a ball. So in the case of binder jetting, for example, they'll talk about being able to produce parts that are, the size of a golf ball up to the size of a baseball or a softball or a volleyball, or even all the way up to a basketball. So we're going to borrow that analogy today, and we're just going to talk a little bit about the particle size of what we're jetting versus other technologies that are out there, like laser powder bed fusion, like binder jetting technology, like slurry-based ceramic additives and such. And basically what we can relate to here in terms of scale is, some very small BBs or steel shot compared to a basketball. And if you think about the particle sizes of what's typically being printed with binder jetting or with some of the other technologies, you're generally in that 15 to 45 micron range, standard metal injection molding or ceramic injection molding powders. Here we're kind of using that analogy to jumpstart a discussion here about a comparison of our inkjet technology, nanoparticle jetting technology versus binder jetting. So they're what we call a second cousin in binder jetting, but we're not binder jetting. And by the way, we're not competing with binder jetting, and you'll see why as we go through the course of the presentation. So the difference here is really that we are jetting nanoparticles directly out of the standard printhead technology that we have with our units. We're jetting in very thin layers, 7 to 10 micron layers, so much thinner than what you would have with binder jetting. In the case of binder jetting, what you're doing is you're spreading that 15 to 45 micron powder in a job box using generally a reverse compaction roller system, and then you're jetting the binder onto the surface of those loose particles to bind those particles together. And then in both cases, of course, you're building up layer by layer. So we're starting with a very clean stainless steel tray that's heated, that's dropping the liquid nanoparticles onto the tray, evaporating the liquid. They're binding the particles that they've spread onto the tray of the job box. All right, so talking here about direct material jetting for both metal and ceramics for the in-use parts. A lot of customers are really interested in talking about what's the resolution of your technology. And so you can see here, we're basically a 1440 DPI resolution printing technology. We're dropping around 120 million drops per second. We are using a piezoelectric technology with our printhead technology. Again, we're jetting in thin layers in the range of around 8 to 10 microns in layer thickness. And so this combination of the nanoparticles being jetted in thin layers with really high resolution is really what's bringing to market the opportunity to fill the gap where a lot of the other additive manufacturing technologies don't quite meet the standards in terms of some of the parts that require really small details, fine feature resolution, very high accuracy, parts again in medical devices and other applications. We can reach obviously a really high density with our green parts being centered, and that is yielding generally very good mechanical properties as well, kind of standard properties that you would see with standard processes like metal injection molding, ceramic injection molding, and such. Here we won't spend too much time on this slide, but just to kind of reemphasize, we have a very unique technology with this ability to jet multi-materials. Again, we're jetting metals metals or ceramics along with a water-soluble support structure. So that's the key enabler to being able to make these really unique geometries and features. So you have freedom of design for cooling channels, internal cavities, overhangs are no issue. Again, very intricate detailed parts that you'll see here as we move forward. We like to give a little bit of a feel for the size range and the capacity of the system based upon the approximate part size that should be under consideration. So we can make anywhere from millions of parts with the capacity of one machine down to hundreds of parts. So again, just like a lot of other additive technologies, it obviously depends on the job box size and the part size and geometry. And so if you have something that's really small, something that, like you see here on the left-hand side, that can fit on the tip of your finger or even on the tip of a ballpoint pen, you can make millions of parts. If you have something that's the size of a pea or a BB, or a small marble rather, you can make hundreds of thousands of those parts with one system. If you have something that's, let's say, a little bit more complex, long in geometry, as an example, we recently made a really nice industrial application with a curved rod that was hollow inside with a little bit of structure, and got very positive feedback from our customer on this application. We can make tens of thousands of those parts. And then if we talk about something like you see on the right-hand side, this internal combustion engine piston application that basically fits into the palm of your hand, you're talking about being able to make hundreds of parts a year with the capacity of a single system with the XJet technology. And so in use here, applications, what can we actually achieve compared to other technology in terms of quality? What you see here is the details in the internal channels, cavities, fine details that you can reach minimum of around 200 microns feature resolution. On the right-hand side, surface finish, we can go down to about 0.8 to 3.2 microns RA for the ceramic materials, and in the range of 0.8 to 6.3 microns RA surface finish for the metals. In terms of part accuracy, again, it's a little bit dependent on part size, but we generally are talking about plus or minus 50 micron part accuracy. If you have a larger part, let's say up to, more in the longer range, like we talked in the previous slide, you can think about plus or minus 1% of the longest feature in that part. However, if you go to the other end of the spectrum and have a fairly small part, we can start talking about accuracies in the range of 20 to 25 microns, plus or minus. Part densities, we basically get pretty much to full density. Ceramics, 99.5+%, metals around 98.5%. Stuck here for a minute. All right. So since this is a center-based technology, it leads us into a discussion about our shrinkage properties, shrinkage factors, comparing that to other technologies that are out there, like binder jetting, like ceramic and metal injection molding. So one of the advantages that we have is because we're jetting those nanoparticles in very thin layers, we get very much less shrinkage, and we get really isotropic shrinkage. So that leads to isotropic material properties as well. You can see the values here in the table. We're going to be in the range of about 15% on average. Each material individually will obviously have its own dialed in shrink factor, and we've dialed it into the 1/10%. So as an example, the 99.99% alumina is 14.5% shrinkage. And the stainless steel is more in the range of 15.5%. Other technologies will be in the low 20s, low to mid 20s in terms of shrinkage, and generally not quite isotropic, again, generally speaking. In terms of sintering temperature, one of the real advantages here with the metal especially is that we can actually sinter at almost 200 degrees C lower, so we're not really approaching the melting point of the metal. And what this is really helpful for is in the sintering process, really minimizes the slumping, the distortion, and some of the challenges that you have with respect to, again, metal injection molding and binder jetting applications. Transition over now to a discussion about the product itself. So essentially what we have is an end-to-end solution. What you see on the left-hand side here is the Carmel 1400 system. So we basically have two platforms of the Carmel 1400C. We have the ceramic system, the 1400C, and we have the metal system, the 1400M. For all intents and purposes, the systems are essentially the same. There's just a little bit of differences in some of the internal aspects of the technology, but the overall size of the platform and all the basic tenets of the two systems are, for all intents and purposes, the same. With that said, one of the questions that comes up fairly frequently is, if I buy a ceramic system, can I switch it over to metal and vice versa? And the answer to that is really no, or at least not very easily. It's not something we recommend. Generally, you purchase a system and you set it up to run one ceramic, one metal, one type of material, and that's what you stick with. So we're offering the system, we're offering the materials. In terms of post-processing, we have an automated smart system. You can see there we've got a ceramic and a metal version of that as well. And so we're basically offering a turnkey solution for end-to-end file-to-part technology that you can take from R&D all the way up to full-scale manufacturing. Just one slide to talk a little bit about CapEx investment comparison. If you look at other technologies that are out there, whether it be binder jetting, laser powder bed fusion, the ceramic SLA, DLP systems, essentially what you'll find with the other OEMs is they have a small, medium, and a large version of everything that they sell. We made a business decision several years ago that we didn't want to go down that path. We essentially wanted to offer and do offer one system that will basically cover all three areas in the development path. So you can buy the same system to do your R&D on the initial part validations. Then once you get the part validated, you figure out that the product is going to work in your application. Now you want to go to medium or small production run, pre-production volumes, and you can do that on the same system with XJet. And then from there, you can ramp it up to the full-scale production system. And you do that with one investment, one system. And one of the things that eliminates is all the challenges associated with qualifying a new powder every time you switch from a small to a medium to a large scale system, and some of the headaches that are associated with that. In terms of cost, you can see some of the numbers that we've estimated here. We can save the CapEx investment, and these are conservative, in my opinion, anywhere from 35 to 50% if we compare to binder jetting or the ceramic-based SLA and DLP machines, and really a significantly less CapEx investment if we compare it to laser powder bed fusion. Now let's move on to just an overview of the process. Some of this we've hit on a little bit already, but if you've got a lean manufacturing Six Sigma mindset, this chart will resonate with you. So if you look at the overall major process steps with the XJet technology, it's really very simple. We start with printing. We go to a support removal through the fully automated smart wash station that we mentioned earlier. And then we go to straight into a debinding and sintering furnace. So it's print, wash, and sinter. If you look at the other powder-based ceramic and metal AM processes, you've got multiple steps that you can see here. The most significant takeaway from this slide is that we have no major debinding operations. So if you're familiar with those debinding operations, whether it's ceramic injection molding, whether it's metal injection molding, or again, some of the ceramic SLA, DLP processes, those debinding processes can take anywhere from 4 or 5, even up to 6 or 7 days, depending on part size, geometry, etc. With our technology, you don't need a separate debinding step. Everything is done straight straight from the support removal, drying the parts, and then into the sintering application. This is just a visual of everything we just talked about. So you can see on the left-hand side here, we have a tray of parts that are being printed. Again, we take that tray out as soon as the parts are finished printing. They can go directly into the automated wash station. From there, we go into a standard sintering furnace. So if it's a metal application, again, we're using standard sintering technology that's already out there being used in metal injection molding. On the ceramic side, standard furnace technology that's already available in the market for ceramic injection molding, dry press and sinter, and etc. I always like to show a close-up of that photo on the left-hand side from the previous slide, just to show the unique technology that we have that really is unmatched in the industry. And essentially what you see here is no loose powder, no loose or open vats of slurry. You basically print what you want. You can print one of these complex parts, or you can print a full tray of complex parts, and you don't have to worry about dealing with leftover slurry, what to do with it, leftover powder, how do I recycle it, how do I re-sieve it, how do I put it back into the process. And again, no major debinding steps associated with this. You can see we actually heat the tray to drive off the liquid as we're building the green parts layer by layer. We're also using infrared heat technology to heat the parts as we build up in the Z direction. Pushing over toward a discussion around the productivity of our parts. This is getting down into the meat of what the engineers always want to discuss and understand with our technology and with any technology, obviously, from that perspective. But we're basically building in the Z direction height around a little less than 1 millimeter per hour. Let's call it 0.7 millimeters per hour. Again, the layer thickness, 7, 8, 10 micron range. Part accuracy, we talked about, plus or minus 50 microns for dimensions up to 5 millimeters. If you've got something that's larger than 5 millimeters, you can calculate 1% of that larger dimension up to 100 microns. Surface roughness, we talked about 0.8 to 3.2 microns RA for the ceramic and 0.8 to 6.3 for the metal. In terms of the densities that we're achieving, basically for ceramics, 99.5% full density, kind of the standard density in terms of grams per cubic centimeter for those particular materials. And then 98.5% for the stainless steel products. The size of the tray for the Carmel 1400 system is 500 millimeters in length, 140 millimeters wide. And then in terms of Z height, our current capability for the ceramic materials is around 50 millimeters, so a little over 2 inches. And with respect to the stainless steel, we're up to around an inch or so, or a little over an inch with 30 millimeters. So roughly 5.5 inches wide, 20-inch long build tray. With that, we're going to pause here, and we're going to turn this discussion back over to Yael, who's going to lead us into the virtual tour of the XJet facility in Israel.
Thank you so much, Harry, for the detailed explanation and introduction of the technology. So now let's go on a tour to our additive manufacturing center where Ron Furman, our AMC manager, is gonna introduce to you about the facility itself and how we make the part that was demonstrated by Harry before, from the file all the way to a mature part. So I would like to remind everybody that if you have any questions, feel free to drop it in the chat box, in the Q&A chat box below, and we'll answer all of them. So feel free. In the meantime, let's start our tour.
Hi guys, how are you? Thank you for joining me for the virtual tour. We are now going inside the additive manufacturing of XJet to see how we produce parts, actually the most interesting parts in the world. So we are inside the additive manufacturing center. I am Ron, the manager of the AMC, and follow me to see the story of we are manufacturing some parts. So actually the story starts for the tray design. So let's design it together. This is the nozzle part. And now we are going to just duplicate it. By the way, we can either print many different parts, or we can take a single part like the nozzle and duplicate it in multiple copies. So now we are going to duplicate it. Let's duplicate it in y-axis and in x-axis. Computer is thinking, and that's it. Okay. We have the parts. We left only with the recipe selection. The recipe is our option to produce parts with different model and support mixture. For example, it will support during the support removal or the sintering. We can create a complete model as a support to support during the sintering stage, or a pure support that will be helpful for internal channels. In this case, the part is pretty easier for our technology. So we will select the standard recipe and we will select build. Now we are heading over to the most interesting part. We are going to start the job actually, and we see how we are direct jetting both model and support simultaneously. So how the technology works, we are direct jetting both model and support materials that our ink is made of nanoparticles, so we are direct jetting both model and support. Let's start the job. So we just press run and start the job. So let's open to see how the story starts. So what we are going to do, we are going to start the job, and we will see how we are direct jetting both model and support. What we are doing, we are jetting on a hot surface the liquid, and all the liquids are evaporating. So we will stay only with the model and the support. So let's see how it goes. So we are printing layer by layer. Every layer is about 8 to 10 micron. And you can take a look how we can start the job. It's the initial process. It takes 1 minute to start the job, and we can see the process starts. We can see how environmental friendly the process, so we can actually open the window and come closer to the moving printers. And now I want you to follow me to see the same job that we started earlier, and it's about 1,000 layers already been printed. It's again the same nozzle that we mentioned earlier. And you can see after 1,080 layers been printed. By the way, we are direct jetting only on demand on the desired shape, almost near net shape. And now I want you to go with me together to see how we perform the support removal. So I want you to come with me, and Aviv, which is one of our expert engineers, to perform the support removal. You can see this tray is the same tray that printed and complete. So we completed this tray, the same nozzle parts. You can take a look how amazing the parts are. And what we are going to do now, we are wash those parts upside down. So we'll put the tray inside the water, and then we are waiting for the water to stream and to remove the support. As you know, our support is soluble, so the water will wash away the support. We are adding some jacuzzi to this process to keep it, to put it a bit faster, and actually to be more comfortable for the parts. And so what we are going to do now, we will leave the parts inside the smart system, and we will see actually the most interesting parts. We will see the parts itself after the producing. And our parts are amazing. The accuracy and the surface roughness are amazing. The accuracy is between N9 and up to N6, which is very smooth. And thanks to our automatically support build structure, we can, and our soluble support, we can print very complex geometries. And to get the amazing accuracy that we can see here, what we are seeing now, we are seeing a report of a GOM scanner that we performed. And you can see the legend on the right side tells the story. Most of the parts are very accurate in the plus minus 50 micron and up to plus minus 100 microns. And this is, guys, how we produce single, 5, 10s, and thousands of parts every day. So this was the additive manufacturing center. And now I want to give you a sneak peek of our R&D. I want you to see the power of XJet. So follow me to see how many machines we have. We have 9 machines here, and their purpose is to produce and develop new materials, new software, and to enhance our capabilities and to improve. And you can see the XJet muscle here, all those machines here, and the amazing technology. And this is it, guys. This is how we produce parts here. So thanks you guys for joining us, and I am adding the mic to Yael. Thank you, guys.
What a great view. I really enjoyed, every time I go down to the AMC Center, I really enjoy the view of all the systems lining up and see the system running and the parts printing. So I hope one day some of you can come over to XJet, to Rehovot, and visit our facility, check the parts for yourself, and then we can explore more business opportunities. So I hope everybody enjoyed this session as much as I did. Now that we have showcased the capability of XJet solutions, you may wonder how could it be translated into business potential, and how could your company benefit from this major shift into powderless additive manufacturing. So allow me to bring Harry back to the podium, and he will share to you the cost calculation model and elaborate the economic benefits of XJet solutions. Harry, please.
Okay, thank you, Yael. Welcome back, everyone. So just to wrap up our discussion, I know a big reason why many of you came to the session today is you wanted to see the results of this challenge part, the one that we talked about having the ability to produce 10,000 parts for this particular application and customer. So here we go. You saw in the video this particular part being printed. The tray that you actually saw was printed in 2 layers. So with our technology, you can actually print in either a single row or with what we call stacked parts. So you can probably tell based upon the video that this part is, well, you can see the dimensions here in millimeters, but let's just say in English units, a little less than 3/4 of an inch long and roughly half inch or a little less than a half inch in diameter. Typically, we would actually print these in many cases just in a single row, just to save time on the system. But I like that we presented the stacked parts option in the video as well. You've already seen this, so I'm going to kind of skip through this. You've seen the top view, the side view. If we just get down to the meat of the matter and what we can actually do with one of our Carmel 1400C systems. So we can fit in a single layer 152 parts. The printing time for that 152 parts is about 20 hours, so a little less than a day. And drum roll, please, we can actually not just print 10,000 parts according to the requirement for our customer, but we could actually print 50,000 of those parts per year. And the approximate cost per part, given everything, is going to be around $6.50 per part. All right, so just to wind things down here and get to our Q&A session, just some of the key takeaways that we want to leave with you today. So the ability to pretty much have design freedom for these internal cavities, cooling channels, overhangs, the fine feature resolution, the high precision parts, excellent surface finish. Again, from an EHS perspective, no powder, no slurry, no major debinding step, and an end-to-end solution for production, everything from R&D to prototyping, all the way up to full-scale manufacturing. With that said, we'd love to see you again in person. If you'll be at the Formnext conference next week down in Austin, come and see us over at booth number 101. I'll be there myself, along with my colleague Gal Raz, who's coming over from Israel. We'll also be at the Formnext conference in Frankfurt in November, as we normally all are in full force with our entire commercial and executive team. A couple of technical conferences coming up is the MS&T conference in Columbus in early October. I'll be attending that, as well as the ASTM ICAM conference in DC at the end of October, first week of November. So with all that, again, we'd like to just say thank you to everyone for attending, and we'll take some questions now, and I'll hand the microphone over to Yael to take us home. Thanks, everyone.
Thank you. Thank you, Harry, for the explanation. So we're giving the microphone to our audience. I see there are 5 questions in the Q&A bar, and let's answer them one by one. Let's start from the first one from Wesley. I actually see Wesley had raised a lot of questions. First one, are you printing both metal and ceramic in multi-material printing? I think this one is what Harry already explained just now. If Harry do you have anything to add on top of?
Yeah, I'd just add something very quickly. It's a very compelling question. It's a question that we get very frequently. Obviously, with the technology, you can jet pretty much anything you want. So we've developed the ceramic ink, we've developed metallic inks. The variety of different inks that we can develop going forward is really, there's no limit to that. And so when you think about applications like printed electronics, for example, this is one area where we see, just imagine being able to print a ceramic part and then deposit whatever metal that you would like in a very accurate position on that ceramic part. So whether it's, platinum, gold, silver, all the types of metals that they use for printed electronics. This is something that certainly is on our radar. We've got really good discussions going on right now with Oak Ridge National Laboratory about collaborating in that space. And we're looking for industrial partners to participate in such a collaboration. So if there's interest there, by all means, would be open to having that discussion.
Great, thank you, Harry. And before we move on to further questions, I would like to introduce two of my colleagues to the podium. I see they're already attending as panelists, but they didn't really actively speak yet. So we have Ron, who was in the tour just now with us, and we have Eyal Duzi, our product marketing manager, on the line too. So I believe that they will be helpful for the upcoming questions. So Eyal and Ron, if you're able to turn on your camera and your microphone, you're more than welcome. Okay, the next question by Wesley is that can you validate the shape and density match of the very small parts with original specifications? I guess Eyal and Ron, this is the question for you. If you are able to explain about it, it will be great.
Yeah, hi, Yael. I hope you can hear me well. So our green parts are quite dense. The density of our green parts gets to around 60%. They are very durable in comparison to any other technology we compared with. And Ron is here with me. If Ron, if you want to add that.
Yeah, the density of the final part, it depends on the material, where our parts are completely dense. The ceramics are really close to the 100%. It's 99.6, and the metal is 97.5 or 98%.
Okay,
And
thank
we're
you.
using GOM scanning, I think, to validate the dimensional tolerances.
Yeah, great, thank you. So the last question that Wesley raised is that when you stack parts, do you separate the wash/debind and sinter? Eyal and Ron, what do you have anything to share here?
Yeah, so we can stack the parts during the printing, and during the support removal, we have the separation of support material, which during the dissolve of the support, the parts are separated. So actually the debinding and sintering is after the parts are already separated.
Great, thanks. I hope, Wesley, that answered your question. The next one is, what's the typical density of the green part versus the final anode parts? Take 316L as an example. Hi, Brendan.
Yeah, we already answered this one. So yeah,
Okay. Great. And then are parts wire EDM'd off the build plate? How are the parts removed for post-processing? Could 0-point system be added to the machine?
Yeah, so actually this is also related to the support removal and our uniqueness. The support is dissolved during the support removal because our support is soluble. So we don't need other technology or aids to remove the parts from for the build plate. So the parts removed spontaneously detached spontaneously from the build plate, and then we are just moving them for the bracket and the next steps.
Yep. Yeah, we didn't really touch on that quite as deeply as I would have liked with the one slide where we're showing the process map. But basically, what Brandon's asking is a comparison to laser powder bed fusion. So in that respect, we cut out a lot of those process steps. Not only do we not have to EDM off the plate, but there's no stress relief of the parts like you would have with a laser powder bed fusion process. Again, no cutting off the build plates. 3 simple process steps: print, wash, dry, and center. If we include drying as part of that.
Great, thanks. Question from Kathleen. What is included in the cost exactly? Does it include material, cost of machine, labor, anything else?
Yeah, I can speak to this one a little bit. Y'all obviously jump in as well. So y'all has been very key in developing our cost model. So the part cost that we showed there really is very comprehensive. So it includes material cost. It includes the cost of the machine. I believe in that particular model, we used a 7-year depreciation for the system. We applied like a 10 or 15% overhead cost, the labor. We didn't really touch on labor as quite as much as maybe we could have, but really with one engineer and one technician, you can have those 2 people overseeing the production of multiple systems, not just one machine. So the labor cost is really minimal, and honestly, the material cost is minimal as well. It's mostly comes down to the overhead and the depreciation being the most significant factors there, as well as obviously the system utilization, which I think we used around 80 or 85% in that particular calculation.
Yeah, maybe to add a bit to your very good answer. So our cost calculation model takes into account fully loaded cost of ownership that includes all the elements as Harry just described. This model doesn't do just the running cost.
Also post-cost.
So it includes also as a full loaded cost of ownership. It includes also the post-process cost as well,
including center.
Yeah, great points.
From the very early start of the process till you get the part itself, including sintering.
Great, thanks. And a question from Markian. Are there any new ceramic materials that are in the works?
Yeah, we are working constantly on expanding our portfolio of materials. And yes, we are developing additional materials. We will showcase some proof of concept samples in Formnext. So come visit us.
Yeah.
Thank you.
Specifically for the dental market. And then what I would also say is when I mentioned earlier this potential collaboration with Oak Ridge National Laboratory that we're in discussions with them about, that's one of the goals or objectives that we would use or leverage perhaps with Oak Ridge, is that they would work with us to develop some of the other advanced ceramics like silicon carbide, silicon nitride, aluminum nitride as a possibility. So great question.
Great question. Okay. Okay, I think this is all the technical questions for our webinar. Of course, I see that there are interest from questions about the questions from the European audience, and for that, you're more than welcome to reach out to us, Wesley, and we'll share with you either the recording or Harry will reach out and share with you the questions or the key points that is raised in the European session. I think this is for the Q&A session. I have to say that I enjoyed a lot in the discussion. And thank you all very much for joining in our webinar. If you don't have any further questions, we are here about to wrap up the whole session. We hope you learned about our technology and solution better now and have mapped in your mind the use cases that it might fit into your business. So if you have more questions, you're more than welcome to reach out to Harry with the details that he shared just now, or you can follow our social media, our website, our newsletter, and all the events that we're having soon, either in the trade shows, for example, Formnext, or in all the other events. So we have a recording for you for this session, and we'll share with you after the webinar. And we look forward to hear from you very soon. So thank you for your time, and see you in our next event.
Just that we will not forget, we will be at Formnext Phoenix. So this is pretty soon, and we are
Austin.
We are welcoming all
Austin.
Austin, sorry. We're welcoming everyone to join us there.
Yep.
Yeah.
Closing comment from my side, just very quickly. I'll just say that I enjoyed today as well. Thanks again to everybody for taking the time. I've actually left my calendar completely wide open for the next 3 days, just so that I could connect with some of you that have attended today and have some interest or applications in mind, so that we can start scheduling some follow-up conference calls even before the end of the week. So thank you again, and look forward to connecting.
Thank you all. Thank you so much for your time, and talk to you soon. Have a great
Thanks,
day.
everyone.
Thanks,
See you.
everyone.
Everyone.
Thanks.
Thank you,
Bye-bye.
guys.